Alright, this is actually section 5.6. It's called inverse trig functions and differentiation. Actually, none of the trig functions have inverses. But we're going to find ways to differentiate them anyway. How come none of them have inverses? Yeah, they don't pass the horizontal line test. Put in a little graph here of a sine curve or something that looks maybe trigonometric. How do I know if something is going to have an inverse? Has to pass the horizontal line test. So if I draw in a horizontal line here, obviously this one does not pass it. Yeah, we can cut it. So in this case, maybe we would start it here and end it here. And then from here to here, it would be passing the horizontal line test. It'd be strictly decreasing in that case. The vocab word for that is what? Monotonic, yeah. All right, so that's why none of the 6 trig functions have inverses. And that is why we have to restrict the domains of all 6 trig functions so that we can find their inverses. And once we've done that, eventually, then we can take their derivative or integrate them, which is where we're at in the next 2 sections. So the first thing I want to do is review for you, or hopefully review for you, how to restrict those domains and what that means for inverses and how we kind of work with them. So this is kind of a review of pre-calculus from last year. So we have a sine curve right here. What is the domain of sine? The domain is all real numbers right now. What's the range? -1 to 1. The range is the y values that are getting graphed, and sine always lives between -1 and 1 in its untransformed state. We need to restrict the domain of sine, though, and we've done that already. What was our restriction? -pi/2 to +pi/2. If we restrict it in that way, then the function is strictly increasing. We made it monotonic over that domain. So the domain we're going to restrict sine to is -pi/2 is less than or equal to x is less than or equal to pi/2. What's the range in that interval? It's still -1 to +1. Remember that domain involves the x variable, range involves the y variable. So let's say you started here and went all the way to here instead. You could, but we're going to define our inverse using this interval right here. So I suppose they could have, and I suppose there's a good reason for why they did. I'll be honest, I don't know why, except for my guess is that so we include a 0 and we have negatives and positives. Just mathematically speaking, probably makes more sense to start it here. Okay, how do I find an inverse? Switch the y and the x. If I switch the y and the x, then that means I'm also switching the domain and range. So for arc sine, what will my domain be? -1 is less than or equal to x is less than or equal to +1. That was the domain, or that is the domain. It came from my range of the original. And then the range is -pi/2 is less than or equal to y is less than or equal to pi/2. You might see that written in interval notation. So that'd be parentheses, -1 to 1. Or maybe brackets, -1 to 1. If we were more awake today, we could probably figure that out. The point, though, is that the domain has to be restricted so that we have an inverse. And once you restrict the domain to find the inverse, the domain becomes the range. And the range becomes the domain of the inverse function. So let's see if we can put together cosine. What's the domain that we need to restrict for cosine? So if I go negative pi to 0, I'll be increasing. But I'm always working with negative numbers then, which is unfun. We're going to define cosine as being from 0 to pi. So that's our restriction. 0 is less than or equal to x is less than or equal to pi. And my range in this case is negative 1 is less than or equal to, y is less than or equal to 1. So for arc cosine then, my domain would be negative 1 is less than or equal to x is less than or equal to positive 1, and the range would be less than or equal to y is less than or equal to pi. Pi day is coming. I don't know. More importantly, we need to observe this and understand where the domain and range are coming from on these. So we have a review in our book on pages 366 and 367. We're going to go ahead and stop and take a look at that review and also pay a lot of attention to the graphs they give us and the domain and ranges for those graphs. Hopefully this will refresh your memory from pre-calculus, and then after we've done that, we'll come back and take a look at these 4 problems. All right, we want to evaluate the arc cosine of negative 1/2. Remember that arc sine, we want to evaluate arc sine of negative 1/2. Remember that arc sine is the same as this notation, which is unfortunate notation. So that's probably why we're going to use this more often than this, because we don't want to get confused with a negative exponent when actually that means inverse sine or arc sine. Okay? All right, so we want to figure out what arc sine of negative 1/2 is. In other words, where is sine negative 1/2 on the unit circle? But we also have to consider where the arc sine actually exists. So we have to go back to what we just did over here with the domain and range. For arc sine, our domain, the value that we plug in, has to be between negative 1 and 1. In our problem, it is. Our answer that we get has to be between negative pi over 2 and pi over 2. So when we get an answer, we have to make sure that it falls within the range that is required. So let's go back to this problem. Where is sine negative 1/2? 7 pi over 6 is one of them. 11 pi over 6 is another. Good, so we have 2 answers here. Now, are either of those in the range? No, because the range is negative pi over 2 to positive pi over 2. This one is outside of that as well as this one. Okay? So that means that we currently have no answer, but there is an answer here. You need to use the unit circle more appropriately. So if I have I can get 11 pi over 6. Yes. 11 pi over 6 radians gives me this that I'm looking for. Okay? But that is not within my range of answers for arc sine. So to get to 11 pi over 6, I have to go 11 pi over 6 this way. Or I could reverse that and go 11 pi over 6 this way, which gets me to positive pi over 6, right? That's not what I have. I went in the negative direction to get there. So actually, negative pi over 6 is my answer. So we need to do a little review of our unit circle. I'll put it over here. We need to remember that. What is that? Okay, yeah, that's the acronym. That's the better acronym for remembering that. But ASTC tells you what about your trig functions? Where they're positive. So in this case, A represents all. All of the trig functions are positive in the first quadrant. This quadrant is sine, but that also corresponds to what other trig function is related to sine? Cosecant. So cosecant is also positive here. Tangent here, but also cotangent, and this one is cosine and secant. Okay, now the other thing that we need to put on here is where our little inverse trig functions exist. As I work my way around a unit circle, this would be pi over 2, and this would be 3 pi over 2, or if I'm going the other way, negative pi over 2. Right? Okay. So we said that sine has to be restricted to negative pi over 2 to pi over 2 in order for us to have an inverse. So the inverse of sine works here. Or in other words, arc sine. We need to be in quadrants 1 or 4. Let's see, pick a different color. Cosine. Where does cosine live? Or arc cosine. So that was sine. If I go back, we had to restrict arc cosine, or we had to restrict cosine, so we wound up with that as our range. So our answers for arc cosine need to be in this region right here. From quadrants 1 to 2. What about tangent? So tangents, inverse tangents graph looks like this. It kind of has horizontal asymptotes, top and bottom. But it exists in the range between these two values right here. What are those two values? It's in your book on that second page. Yeah, it's negative pi over 2 to pi over 2. So this is also inverse tangent, or arctan. So those are where our answers need to live. For sine and tangent, quadrants 1 and 4. For cosine, quadrants 1 and 2. So if you can keep those straight, just keep remembering ASTC. Keep those straight, hopefully. This little drawing right here will help you come up with where your answers need to be. Negative pi over 6, arc sine, we're in the first quadrant. No, sorry, we're in the fourth quadrant. We went the other way so that we could land in the first quadrant. Because we went the other way, we make this sign negative. Okay. How about arc cosine 0? Another way you can think of doing these problems is making it an equation. Y equals arc cosine 0. If I make it an equation and I want to get rid of arc cosine, then I can apply cosine to both sides. Because cosine of arc cosine wipe out their inverses, right? So then I have cosine y equals 0. Where is cosine 0? Pi over 2 is one of them. Anywhere else? And also 3 pi over 2. But is 3 pi over 2 in our range of values that we can get as answers? No. But pi over 2 is. Pi over 2 is between 0 and pi, which is where our range of answers can be for cosine. So therefore, pi over 2 is our answer. How about arctangent square root 3? By the way, notice that all of these problems so far have been problems that we can find exact answers for. You always want to try to find exact answers, if possible. So with this arctangent square root 3, and I know that square root 3 exists on the unit circle, this is asking me for exact answers for sure. So I want to try to figure that one out. Where is tangent the square root of 3? Pi over 3? Well, hang on. Let me redo this here. I'll make it y equals, and I'll apply tangent to both sides so you can see that what I'm actually looking for is where is tangent the square root of 3. So on our unit circle, we're looking for square root of 3. It's not on there, of course, but we know that tangent is sine over cosine. So maybe I'll just pick one. You're right, by the way. But I want to pick pi over 6. Let's say it's pi over 6. If it's pi over 6, then the coordinates at pi over 6 would be the square root of 3 over 2, comma, 1/2. And because tangent is y over x, which is sine over cosine, y over x, so I'm going to go with this guy divided by this guy, 1/2 over the square root of 3 over 2. If I leave it, change it, flip it, then this becomes 2 over root 3 and multiply across, and I get 1 over the square root of 3, which is the square root of 3 over 3, which is not what I was looking for. So pi over 6 does not work. Try pi over 3. At pi over 3, these two coordinates right here are actually flipped. So now we have, so for pi over 3, that gives me the square root of 3 over 2 divided by 1/2. Leave it, change it, flip it here. The 2's will cancel, and I'm left with the square root of 3. So that means that you found it. It is pi over 3. And how about that last one, arcsine 0.3? Do we have a 0.3 somewhere on the unit circle? 3/10? No. In this case, because we're not dealing with easy numbers that we know are on the unit circle with that 0.3 right there, basically that's a calculator problem. You're looking for the sine inverse function button on your calculator, and then just type in 0.3 and press enter. Make sure that your calculator is in radian mode. The calculators in our room always default to radian mode, so you shouldn't have any problem there. But what do we get? 0.3046, and we round to 0.305. 3 decimal places are appropriate here.